Hello everyone. As mentioned previously to Henry, I would say good morning, but I think for a great number of people, that's probably not quite correct. Suffice to say, thanks for joining us for this webinar on time-resolved ARPEs. It's really good to see quite a large turnout for what I know is going to be a pretty informative presentation. My name is Peter Airy, and I'm a product specialist for nanotechnologies for AXT. Before I sort of go too far, I probably need to make a special mention to Materials Australia. They're an organisation here in Australia. They assisted in disseminating the webinar to the members, so it was very kind of them. I'm pleased to open the introduction to this webinar, conducted by AXT in collaboration with Henry Captain and Margaret Murnane. I'll be pretty brief, but for those of you who don't know, AXT is a pretty dynamic distributor for high-end scientific instrumentation in Australia and New Zealand. We have a pretty large product range covering everything from microscopy, microanalysis, nanofabrication, and nanotechnology. And we take great pride in collaborating with both researchers and suppliers to provide the latest in scientific instrumentation. And this is especially the case with KM Labs. About the presenters that we have for you today, for those of you that didn't read the abstract, which is probably a good number, Henry and Margaret are professors of physics at the University of Colorado in Boulder. They're fellows of GILA, which is a research institute joint between the University of Colorado and NIST. Together they won the Benjamin Franklin Medal, congratulations, in 2020. Henry is a member of the US National Academy of Sciences, and Margaret is the director of National Science Foundation, the STROBE, which is the Centre for Real-Time Functional Imaging. So I suspect they're fairly busy people, so I appreciate them being able to present us their latest on this. They are more than happy for anyone to have any questions, just to flick it in chat or put their hand up during the presentation. And I guess that's probably enough from me. I'll hand over to Henry to get things going. So all yours, Henry.
Okay, well, thank you very much, Peter, for that introduction. And the way we're going to do this seminar is I'm Henry Captain, and I'll start out this seminar and tell you a little about our light sources, and then I'm going to hand it to Margaret Murnane, who's right here, and she will tell you about some of the physics that is possible to do with these new light sources. So the topic we're going to talk about is on time and angle resolved photoemission and applications in materials science and materials research. And this work is a mix of work from our team at the university at GILA, and we have quite a number of very enterprising graduate students and postdocs who have contributed to this. Also collaborative with our company KM Labs, and we have a number of different types of light sources that we've been striving to commercialize and to make usable for a broad spectrum of potential applications. We also have quite a number of collaborators worldwide. So just a brief outline, I'm going to tell you a little bit about the technique we use to generate very short wavelength light for photoemission. It's called high harmonic generation, and it really has come into its own as a versatile light source in the past decade or so. We use femtosecond lasers to generate this light, which makes it ideal for time-resolved RPs, or time and angle resolved photoemission, also for quite a number of applications that I'll just briefly mention. I will tell you about some of the things that are upcoming. We have new light sources, and other startup companies have developed new detectors for angle resolved photoemission that will allow for very high fidelity and spin resolution. And finally, Margaret will tell you about how we can probe electronic structure and interactions with both static or conventional angle resolved photoemission and with time resolved photoemission. You can map band structure, you can understand interactions and energy flow in materials to ferret out what the interactions are, and by seeing what their time scales are. There are also potential technological applications like looking at band bending in junctions, semiconductor junctions. So, you know, as we all know, lasers have been around for quite a while at this point, 60 years, but, and in fact, this is the 60th anniversary of the first demonstration of the laser by Ted Mayman. Now, if you look at the history of laser technology, one thing that has been frustrating to some of us is the fact that that wavelength in terms of laser technology has been one of the areas of slow progress. So for example, the very first laser, the ruby laser, operated in the red region of the spectrum, right around 700 nanometers. And if you look today at lasers in widespread use, the biggest application of lasers at short wavelengths is for photolithography in the semiconductor industry, and they use a wavelength of about 200 nanometers. So it's less than a factor of 4 decrease in the wavelength of sources over 60 years, with the exception that we've now developed techniques to upconvert laser light to shorter wavelengths. And that's what we're using here is a technique called high order harmonic generation. It allows you in a single conversion step to combine dozens or hundreds of photon, take the h nu from a photon from a laser and combine a large number of photons to get a smaller number of high energy photons. So how does that work? Well, this is a process that was first discovered in the late 1980s. So it is relatively a recent phenomena, and it also a fundamental property of an atom that if you shine very bright light on it in a very short pulse, you can easily take a femtosecond laser and focus it to the point where the electric field corresponding to that focused laser is comparable in magnitude to the electric field that binds an electron to an atom. So you focus that laser into a gas and you get a field ionization process. Now that process was studied since at least the 1970s, but the big surprise in the late 80s is that people discovered that if you did this, you could also see a beam of coherent upconverted light at much, much shorter wavelengths than the driving laser. And the mechanism for this is this kind of boomerang trajectory for the electron. Because you're illuminating these atoms with an oscillating electromagnetic field from the laser pulse, field ionization is followed by an oscillating trajectory of that ionized electron. And sometimes these electrons can come back to the vicinity of the ion, their parent ion, and undergo a free to bound transition, go back into the electron goes back into the ground state. That means that electron stops abruptly, and that abrupt motion causes the generation of much shorter wavelength light. So it's this so-called recollision trajectory that allows you to generate harmonics, and the characteristic of it is that you see in the simplest manifestation, you see these odd order harmonics, the third order, fifth order, seventh order, all the way up now to more than 5,000 orders. Although at that point, we're not resolving individual harmonic orders anymore. This process has really developed dramatically in the past 15 years or so, to where we can make very, very broad super continuum, in other words, a continuum spectrum that doesn't even show harmonic peaks, or you can make very narrow peaks depending on the types of lasers that you use. The temporal coherence of this light translates from the laser into the high harmonic light. So you have a full temporal coherence. Now that doesn't mean that the coherence length of this light is very long. What it means is that it's actually structured to give very short pulses of light, femtosecond and attasecond. So if you hear the term attasecond science, that is basically science done with high harmonic generation. And there are even some more recent measurements and theoretical proposals to go to actually probe at zeptosecond timescales. What you do with a zeptosecond, who knows? It's up to the imagination now, but it's certainly exciting. The spatial coherence is also excellent. You can control the polarization state of the light, and it really has some unique characteristics, much more versatile in terms of the coherence characteristics than you get with either a conventional X-ray tube or with the synchrotron light source. So we really have exquisite control over this laser light. And with new laser technologies, you can also get quite good flux for applications such as angle resolved photoemission. So without going into details with this, high harmonic sources are an alternative light source to large scale synchrotrons. They're more complementary than they are a replacement in that they give you time resolution. If you want energy resolution, you're maybe better off going to a synchrotron, but there's a lot of progress in this area too. And these sources do have the huge advantage of being tabletop scale, and thus you can have them in your lab. And that really is the huge benefit that we see in doing research, is that instead of having a week, a year at a synchrotron, our students can actually accumulate data for hundreds or thousands of hours in some cases. And that allows a lot of experimentation, a lot of alternative setups and techniques that can really accelerate the pace of science. So now I'll tell you a little bit about photoemission. In angle resolved photoemission, what you do is you illuminate a flat surface with quasi-monochromatic light, generally in the ultraviolet or vacuum ultraviolet region of the spectrum. So you want to be above the work function of the material, and you want a very flat surface, which generally means a single crystal surface. What happens then in the photoemission process is that you absorb a photon. An electron in the material absorbs a photon. Suddenly it has a lot more energy. It's moving faster. Some of those electrons encounter the surface of the material. And if they have energy that exceeds the work function, they can actually go over the work function barrier into free space. And if you look at what happens to the direction of motion of those electrons, it's very much like a Snell's law. If you have an electron going through a flat surface, the component of of momentum perpendicular to the surface changes, but the momentum parallel to the surface is constant. And what that allows you to do is by looking at the angle of emission of those electrons, you actually get a map of the band structure of a material, or something that's very, very close to the band structure of a material. And here's a simple example of angle resolved photoemission done with a laser, where you see band structure, in other words, K vector versus energy, all the way up to the Fermi level of the surface. And this is very simple, but you know, some of the considerations that you have to be cognizant of are, for example, the wavelength or the energy of the photons that you're using for photoemission do constrain the photoelectrons that you can see. In other words, you actually need an energy exceeding the work function in the direction of perpendicular to the surface to get the electron out. And that means that for angle resolved photoemission, if you want to get a full picture of the valence band structure of a material, the ideal energy of the photon is 10 eV to 40 electron volts is generally the range where the best RPs is done. If you have very long wavelength light, like ultraviolet photons from a conventional laser, you may be able to get photoemission, but only for photoelectrons that were traveling pretty much in the direction toward the surface to begin with. So you only get a partial view of the band structure of the material. You know, if you use high harmonics for this, now you have pulses of light. You can get time resolution with vacuum ultraviolet light, such as we get with high harmonic generation. Then you can map the band structure across the full Brillouin zone. And if you add a pump pulse to do pump probe spectroscopy, you can access, for example, the unoccupied states of a material, or how the band structure of a material changes as it goes through a phase transition. Also, how electrons, phonons, and spins are coupled in a material. So there's a rich variety of information that you can get by doing pump probe studies with angle resolved photoemission. And that's on top of the large body of work in RPs done in a non-time resolved fashion. Now, this picture here on the right shows band structure in a material and how, after excitation with a pump pulse, you can now see electrons in an excited state band. This is also accompanied by a phase transition here. Now, KM Labs has been working to commercialize this technology. We've developed a system called the ZEUS, Extreme Ultraviolet Ultra-Fast Source. One example of a customer is IMEC in Belgium, the International Microelectronics Consortium. They are installing a system to use in support of extreme ultraviolet lithography. The industrial interest in these sources has allowed us to really advance toward routine use and industrialization of these high order harmonic generation sources. The source is a combination of the femtosecond laser system, and you want a high power because the conversion efficiency for high harmonics varies between 10⁻⁴ and 10⁻8. So you want to start with a whole lot of photons. You get a lot of photons out, plenty to do these experiments, but you do want an advanced femtosecond laser. And then there's the frequency conversion step and the beamline, which is what we've commercialized in the Zeus 4, which is shown in a picture down in the corner there. Here are some examples of the performance of the system. You can actually take the laser, which is an ultra-fast high sapphire laser, and use that output directly to get a comb of harmonics with relatively broad spectral bandwidth for each harmonic. So you would use a simple monochromator to isolate a single harmonic peak. On the left is another example where what we did was frequency double the light pulse. It turns out that for high harmonic generation, the shorter the driving laser, shorter the wavelength of the driving laser, the lower the photon energy of the high harmonics, but the high harmonics are spaced out nicely, so you can inherently get almost completely isolated single harmonics. And in this case, there's one harmonic at the 7th harmonic of 400 nanometers is at 22 eV, and that's a great photon energy for RPs. So there's flexibility in how you can do this. You can also rotate the polarization of the laser to rotate the polarization of the light source. This is a typical setup. You take your Ti-Sapphire laser, that's a KM Labs Rhea laser. You take part of that, the beam from the laser, and you use it as a pump pulse. You have a delay stage in there, so you can vary the pump probe delay. Then you use the majority of the light to drive the higher order harmonic generation process. You have some optics to eliminate the co-propagating laser light and to select a single harmonic. Then you would have the pump and the probe hitting a target, generating photoemission that is then picked up by an analyzer. And work to date has generally used 2D spherical angle resolve photoemission systems. And there are very many of these around worldwide, and they're all amenable to use with high harmonic generation sources. Now, another emerging development is a new technology that KM Labs has developed for generating VUV light at megahertz repetition rates. This actually uses a very different setup. It's a system called the Hyperion VUV. It's a smaller system, generates light at much higher repetition rates, which is useful for avoiding space charge distortion of the energy spectrum. And it also gives very high flux over a bandwidth ranging up to about 15 to 18 EV. Now, this source actually is very promising to use with new types of detectors. So time-resolved RPs detectors, and there are several types of them out in the market now, are very interesting as a new direction that still has a lot of untapped potential. This is just some examples of what you get from this source. The flux is highest at lower photon energies. It decreases toward high energies, but it's still quite bright even beyond 10 eV. To date, this is very developmental. We've done about 3 of these units so far, and its use in RPs is as yet untapped. But one thing that we're very excited about implementing is that there are new ideas for implementation of the angle resolve photo emission spectroscopy that will allow for spin resolution, so that you could not only get the energy and momentum picture of the band structure, but look at spin for magnetic materials and spintronic materials. And this is a startup company that we're starting a collaboration with to demonstrate this technology. It's a very efficient instrument because it uses the time structure of the laser specifically to allow for very high data acquisition rates. So it's a different technology than is used at the synchrotrons, and it's ideally suited for use with these megahertz rep rate laser sources. Now, looking at the applications of high harmonic sources, this is a montage that shows some of the work we've done in our labs. You can look at spin dynamics using both photoemission and also magneto-optic Kerr effect. We've done a lot of work in energy transport at the nanoscale that uses these high harmonic sources simply for their short wavelength and short pulse duration. Has had very remarkable results. You can implement new types of coherent microscopy with short wavelength light. And those microscopies have the potential for element and compound specific information. But, you know, the big use is for, that we see as turning on earliest is for time and angle resolved photoemission studies. And with this, I'm going to turn things over to Margaret, who will give you a couple of examples of this. So,
thank you, Henry. So I'd like to talk about what new information one can learn about materials by implementing time-resolved RPs. And in the past, the traditional view of using ultrafast lasers to study materials relied on the fact that depending on the coupling between the different charge lattice and spin baths in the material, if you perturbed the material with a femtosecond laser, you could look at the time response and understand something about the interactions. When you heat a material with an ultrafast laser, the heat capacity of the electron gas is much smaller than that of the lattice. So they, as shown here, their temperature spikes, and then with electron phonon coupling, the lattice heats up and the electron bath cools in about a picosecond or so. And that understanding has been the norm since the mid-1970s. And what's very interesting is that we've shown, and this understanding was also assumed to be true in magnetic materials, where the electrons absorb the energy and then lost energy to the spins in the lattice through different coupling mechanisms. But one criticism that people said is that if you heat a material with an ultrafast laser, it's like whacking a delicate quantum material with a hammer. You know, you're putting everything out of equilibrium. And could you learn anything about the non-highly excited states, anything about the equilibrium material? And hope to show you in the next 5 minutes or so that yes, you can. And in fact, that previous understanding about the laser energy being absorbed by the charges and then relaxing to the lattice and the spins is actually not correct. In fact, the situation is much more exciting and interesting from a physics point of view. So the way to think about it, and this is something we've shown now in several systems, is that the heat capacity of the electrons is smaller than the lattice. So if you monitor the electron temperature, whenever there's a change in coupling or a phase transition, you should see a jump in electron temperature. And we're seeing that that is allowing us to find new excited states in magnetic materials and make beautiful maps of 2D materials, charge density wave materials, because it allows you to find hidden phases that you could not see otherwise. So let me explain and also look at the manipulating electron phonon couplings and driving lattice distortions that you just can't get to by dopant or strain. So they're quite interesting in opening up the phase diagram of these advanced materials. And so the example I'm going to give you is in a charge density wave materials that are very interesting 2D materials. 2D materials in general are very important because we can tailor their electronic and photonic properties. And they're also very interesting from a physics point of view because charge density wave order is often close to the phase space of superconductivity. So in charge density wave materials, the previous understanding was these were materials that in their normal or melted phase, the electrons and atoms are uniformly distributed, but at lower temperatures, the system can undergo a phase transition to charge density ordered phase, become insulating, where the both the charge, the electrons, and the atoms have relaxed into this state here on the left. Using ultrafast RPs, we actually found two new phases, a new light-induced relaxed charge density wave order and an inverted metallic charge density wave order. So the material we looked at, and we've looked at many materials, we see these phenomena in them, but the one I'm just going to talk about this evening or this morning for you, for those down under, is tantalum diselenide. It's a beautiful material that in its charge density wave phase relaxes into a Star of David order. And so what we do is we heat this material with a femtosecond laser. Because the charge density wave order is in the ground state, the electron orbitals in the charge density wave state are located, you know, around. I mean, they screen the atoms and give rise to this beautiful order. But the excited state orbitals are delocalized. And so when you heat this material with a femtosecond laser, you promote electrons from the occupied to the unoccupied states, and they very beautifully excite a coherent phonon or a breathing mode of that Star of David. And that's been seen before, and so that is not new. What was new is, so in the past, people knew about this charge density wave state and the normal phase and the fact that you could melt this order with a femtosecond laser. What we found is that by smearing the charges, we could actually put the material in any phase in between. Not forever, it lasts only about a nanosecond, but it's still information about the material and about the ability of light to manipulate a material that was not known without using time-resolved RPs. So this is some of the data. So in the insulating state, there's a band gap, and if you take the material and you excite it, you see these characteristic oscillations, and that corresponds to that breathing mode of the Star of David. If you heat the material then with a femtosecond laser, you can drive it above its transition temperature, the band shifts, the gap closes, and this characteristic band shift goes from the band shift corresponding to charge order to correspond to the melted phase. What was interesting though is that by adjusting the laser fluence, we could place the material in any state in between. And to see what that was, we used time-resolved RPs to map out the electron temperature as a function of time. And we found this very curious behavior that as we heated the material with higher and higher laser fluence and looked at what the electron temperature was at different times, what we would see is that at a certain fluence, the electron temperature would suddenly jump. And in this case, by hundreds of degrees Kelvin, as we increase the laser fluence. Now, normally, with a fixed heat capacity, as you put higher and higher laser fluence on a material, it should get hotter and hotter. This jump in temperature meant that there must be a change in heat capacity. And in fact, the heat capacity one has to assume to come up with this higher temperature, that heat capacity is 1/3 the equilibrium heat capacity. So what we think is going on is that we heat these quasi-2D materials with a laser. Initially, only the strongly coupled phonons and a subset of phonons well, initially the electrons are heated, but then they lose energy only to a subset of strongly coupled phonons and other strongly interacting phonons. The cross-plane phonons are not excited, and so because we are exciting only a subset of phonons, the heat capacity of the material drops, and also the potential charge density wave states that we can access open up. And in fact, we can look at that with angle resolved RPs. We can see that sure enough, in this intermediate state, there is a band gap, so it is a charge density wave state. We also learned other very surprising things about the material. This is RP spectra at the Fermi level as a function of time. And when we translate that into an electron temperature and a band shift map, what we see is something very surprising. We see that the electron temperature is oscillating in phase with the amplitude mode, the strongly coupled phonon mode. And these temperature oscillations are quite high. They go between 200 Kelvin and 1,000 Kelvin. And so what we're seeing is that as the amplitude mode is launched, that it's modulating the density of states and band structure that is pushing electrons around and changing their temperature. And so we because the behavior is different when we gently excite the material compared to when we strongly excite the material, we can just with angle resolved photoemission learn something about how the phonons and electrons are talking to each other. In some cases, interacting coherently, in others, incoherently, in other cases, inducing anharmonic decays. So what we learned is two temperature model does not work for strongly coupled materials, and there's some beautiful ways one can manipulate these materials with light. And I think at this we go to 5 minutes. Is that right, Peter?
Yep, thereabouts.
Yeah, one more topic.
Okay. So then I will switch to just the last topic I would like to talk about, which is a related topic. It's related to layered materials, this idea that we can actually look at layers and interfaces by using the same light source, the high harmonic Zeus light source, and combine it with coherent imaging. So essentially what that allows us to do is, for the first time, we can build a near perfect X-ray microscope, because we can use the coherence in conjunction with powerful phase retrieval algorithms to actually build an image, instead of using an X-ray lens, which essentially is a diffractive zone plate optic. These are very challenging to make with high fidelity, but by shining the high harmonic beams on a material and then analyzing the scatter pattern, we can look at buried interfaces. We've achieved the first subwavelength imaging. We can do dynamic imaging, look at energy flow. And the thing I would like to talk about is just, for one slide, is to talk about a non-destructive approach for making a 3D map of a material with composition, layer structure, and interfacial information. So the challenge we're trying to address here is that in many heterostructures, you would like to know the dopants, the interfaces, You can do that with electron microscopy. It's absolutely stunning images, but you can't do it in situ. What we did was to build what we called, essentially it is an imaging reflectometer. So we scan the angle and make images, and that has allowed us to make these really beautiful 2D and 3D rendered maps, where all of the colors here, the light purple, green, gray, even pink here, that all corresponds to a different material or a native oxide or such. And we're very excited because it is something that would be useful. This sample was made for us by IMEC. And compared to other approaches, it has advantages over SIMS, atomic force microscopy, and electron microscopy. So we get very nice non-destructive maps of the structures and dopants. And so with that, I want to thank you for taking the time to listen from halfway around the world. I hope we've given you just a very, a brief introduction to show that harmonic light sources, they're a unique quantum technology, and they're very useful. We can learn things about materials, heterostructures, and about the beautiful physics of strongly coupled materials. And everything scales with the wavelength, so this technology has a long way, can go a long way. And I'd like to, in particular, thank the student and postdoc team who was responsible for much of the work we talked about, as well as our collaborators. And thank you very much for your attention.